when you've been studying physics, there's something you've probably not heard in your classes, and that's a neutral pion is equal to relativistic positronium. And that's because this alternative view of a neutral pion, which is sometimes referred to as a Sternglass pion, because Sternglass was one of the discoverers, has been suppressed by the quark theorists. They don't want people to know that there's an alternative particle theory that's particularly important to the lowest energy mesons. So I'll walk through it, and even bigger is that once you have this Onium theory, and the Onium is part of the Positronium work, then you have a greater theory of particles that only requires electrons, positrons, protons, and antiprotons to be present, and there's no need for quarks at all. To begin with, what positronium is when you have an electron and a positron in orbit. And when they orbit, they have the Coulomb attraction that you would expect pulling them together. But if they orbit fast enough, you get a relativistic force pulling them apart. So positronium occurs as a metastable state when the centrifugal force opposes a Coulomb force, and that they're equal, briefly. Positronium doesn't exist for very long, but it has been observed and experimented with on the low energy side. But what you don't hear very often is that there's two different positronium solutions, or two different energies. There's actually a couple depending on the spin state of the electrons, whether they're opposite or aligned. But I don't need to really go into that. There's a low energy state, which is studied and well known, but there's also a relativistic state. And the relativistic state is much higher velocity, so much so that the relativistic mass of the particles has increased significantly and increased the mass. So relativistic positronium is much more massive. And in fact, it has the mass of a neutral pion. So the initial discoverer of this was Milne, and he published it in a book he wrote in 1948. But his theories were not really popular, and this was toward the back of the book, and it's not really clear how many physicists actually were aware of it. And then in 1960, Ernest Sternglass decided that he wanted to try to model a pion as a proton-electron composite. And he approached Richard Feynman, who they knew each other from their time at Cornell, and Feynman suggested that he start with the electron-positron and see what that does. And so Sternglass was in Feynman's office at Caltech, and he just worked it out on the board, and they worked it out together, although Sternglass was doing most of the work from the way he wrote about it. And when he was done, he found out that this was a classical model or semi-classical model of a neutral pion, and Feynman recognized that. And a year later, Sternglass published it. He had refined the measurement from 140 MeV per c squared down to 134.7, which is fairly close to the known value for the mass of the pion today. And keep in mind that was 60 years ago. And it's quite certain that quantum field theorists could refine the calculation more to get a more precise measurement showing that relativistic positronium mass is equal to the neutral pion mass. And so we can compare that to what happens in the quark model. In the quark model, a neutral pion is supposed to be an up and anti-up quark minus a down and anti-down quark divided by the square root of 2. Well, the first thing to realize is that when you put together an up and anti-up quark, they annihilate and leave nothing. When you put together a down and anti-down quark, they annihilate and leave nothing. And you might say, well, maybe there's an Onium compound with the up and anti-up quark. Well, they've never been detected, never been observed. So, no, there isn't one. And is there an Onium compound with the down and anti-down quark? No, there's not one of those either. So, to start with, you have nothing minus nothing divided by the square root of 2. And of course, nothing divided by the square root of 2 equals nothing. And even if you did have an elementary particle that was somehow left after these two pairs of particles annihilate, you can't subtract one elementary particle from another elementary particle. That makes no sense. They couldn't be elementary particles if you could subtract part of one from another. And then they can't be elementary particles if they're divisible by the square root of 2. So this whole model that the quark theorists came up with has no basis in physical reality. It's something manufactured to try to get the decay modes to work out, but it has nothing to do with reality. And now one of the really great things about this model is that you get a value of the mass. It's the number of particles, 2 in the case of positronium, times the mass of the electron divided by the fine structure constant, which is the inverse of 137.036, roughly. And so when you do that math, it equals almost exactly 70 MeV per c squared per particle. And since you have 2 particles in the pion, it's 2 times 70. It gives you a mass of 140. Well, it turns out that all of the mesons and baryons are quantized the same way, although some have quantization states in the 35 MeV per c squared range. So in the case of the ones that are quantized at 35 MeV per c squared, that's the mass of the electron divided by 2 times the fine structure constant. So what you can do is you can look at the decay products of all the mesons and baryons, determine how many pions are in there. If you break it down into how many pions it would have to contain to account for the most complicated decay modes. And then you can multiply it times the energy and determine the structure of the compound, and how many pions it contains and how they're combined. And using that approach, you can model all of the unstable particles, which I prefer to call resonances, because if they're compound, they're not really particles, they're resonances. But the simplest resonance is the neutral pion. And if you have a theory of particles, you have to get the simplest and lowest mass particle right before you can move on to any of the others. And this is a case where the Onium model that was begun by Milne, Feynman, and Sternglass is far superior to the quark model. And the quark model also has 6 other low energy mesons that have this nonsensical formulation. The other mesons with this nonsensical formulation include the rho, which is identical to the pion for some reason. That's impossible because their decay products are different. And the omega. And with the rho and omega, one is the rho is subtracted while the omega is added, yet they have almost the same mass. While the eta and eta prime has some quarks added and some quarks subtracted. And there's a big mass difference between the eta and the eta prime. So the whole system of addition and subtraction, when it appears like it might work, doesn't work. And then the other two are the k long and k short, where once again you have addition and subtraction, but somehow they have the identical mass. So the whole thing is a bit of a nonsensical joke. But I'll do another video on the other six, although I may even break those up to go into more detail. Anyway, so when you are learning about particle theory, think about what the neutral pion is and the Sternglass model. And as I said, I'll be doing a lot more videos on Onium theory. I discuss it in far greater detail in my book, Goodbye Quarks, the Onium theory. I also have some technical papers, and I'll attach a few if you want to get a taste of what the model's like as a whole. And I have a couple other books on quantum field theory that you might find interesting as well. So I hope you liked the video. If you did, please like, share, subscribe. And I'm an independent researcher, so if you want to feel like you want to support my research, you can do that by buying my book, or I have a Patreon account that's listed below. So thanks for watching.